Hey everyone, and welcome back. Today we're going to talk about something you use literally every single day, but probably never give a second thought to: the humble electrical cable. It turns out there's an absolutely incredible world of engineering hiding in plain sight, right there inside your walls. So let's just jump right in with a puzzle. Why is the wire powering a light bulb in Mumbai constructed in a completely different way from one in London or New York, even though it's doing the exact same job? The answer to that question, well, it reveals a fascinating story about global engineering, convenience, and some pretty serious hidden trade-offs. Okay, before we solve that, let's just set the stage a little. These ordinary household cables, they are the true unsung heroes of our modern world. They are that final, critical link, the last mile, that brings all that power from the massive grid safely into our homes, into our lives, into our devices. And this isn't some kind of wild west of wiring. Oh no. This massive, unseen network is governed by incredibly strict standards. Think of them as rule books, like IS 694 from the Bureau of Indian Standards, or the global IEC 6027. These documents dictate every single tiny detail of a cable's design to make sure it's safe, efficient, and gonna last for decades. So what are these standards actually regulating? What is packed inside these things? Well, let's do it. Let's peel back the layers and actually deconstruct a cable to see all the technology that's packed inside. At its core, every cable really has three basic parts. On the very outside, you've got the sheath. Think of it as the cable's tough protective armor. Underneath that, you have the insulation. This is the absolutely critical safety layer that stops the live wires from touching each other and, causing chaos. And then, at the very heart of it all is the conductor, the metal superhighway that carries the electricity, almost always made of copper. Okay, now here's where we get to the absolute core of our mystery, because it's not just the material of the conductor that matters, it's its physical structure. In the engineering world, this is known as its class. And believe me, this changes absolutely everything. And you can see the huge contrast right here. Think of a Class 2 conductor like a thick, sturdy rope made of just a few heavy strands twisted together. It's strong, pretty rigid, and it's perfect for things that are installed once and never move again. But then you have Class 5, and that's more like a fine thread made of hundreds of tiny, delicate hair-like wires all bundled together. It's incredibly soft and flexible, designed specifically to be bent and moved around. Two totally different approaches to carrying electricity. And this fundamental difference in design has led to a major split in how the world wires its buildings. And this brings us right back to the core paradox we're trying to solve. See, in most of the world, we're talking Europe, North and South America, the regulations are very clear. For the permanent wiring inside a building's walls, you must use the rigid Class 2 conductor. And the logic is solid, right? It's mechanically tough, and its thicker strands have less surface area, which means less oxidation and breakdown over a 50-year lifespan. But here's the twist. In India, the market made a massive, massive shift. Today, the standard for permanent house wiring, again, the wires inside your walls that never ever move, is the super flexible Class 5 conductor. So what gives? Why on earth would you use a wire designed for constant movement in a completely fixed application? And the answer, as it so often is with engineering, comes down to a classic trade-off. See, Class 5 wires are an absolute dream for electricians to install. Because they're so flexible, they can be pulled through tight twisting pipes, conduits, much, much faster. It saves a ton of time and labor. But the trade-off is that the rigid Class 2 wires are just a little bit more efficient. Their compacted structure packs in more copper, which means just a tiny bit less electrical resistance. Now you might be thinking, a tiny bit of energy loss, who cares? And for one single home, you'd be right. It's basically nothing. But, and this is the crucial point, this choice matters at scale. You multiply that tiny, insignificant energy loss by millions and millions of homes across an entire nation, and that simple choice for convenience leads to a real, measurable, systemic increase in national power consumption year after year, a fascinating and massive consequence of one small engineering decision. Okay, let's shift from the conductor to the second layer of genius in our cable, the insulation and the sheathing. This is all about how advanced chemistry keeps us safe from disaster. So these protective layers are usually made from PVC, but this is not the simple plastic you might be picturing. Raw PVC is actually rigid and brittle, completely useless for a cable. To make it work, chemists create a complex cocktail, heavily compounding it with plasticizers to make it flexible and thermal stabilizers to stop it from breaking down during the incredibly hot manufacturing process.
This chemical engineering also creates different grades of fire safety. You've got your standard PVC, which is fine for most uses. Then there's flame retardant, or FR, which is specially formulated to stop a fire from spreading along the wire. But the absolute top tier is FRLSH. In a fire, it not only resists flames, but also emits very little toxic halogen gas and very little of that dense black smoke. And that's why it's legally required for places like subways, data centers, and skyscrapers. Because in evacuation, being able to see and breathe is the difference between life and death.
So, how in the world do manufacturers apply these complex polymer layers onto the conductor with such perfect microscopic precision? The answer is a high-pressure, high-temperature process called extrusion. And the cleverness here is just brilliant. For the inner insulation, they use what's called a pressure die. It forces molten PVC at 200 degrees Celsius directly onto the bare copper, creating a perfect, tight bond. But of course, you can't use that same intense heat for the outer jacket because it would just melt the inner wires you just finished coating. So for that layer, they use a tubing die. It extrudes a loose tube of PVC around the inner cores, and then a powerful vacuum instantly sucks it down into a tight, perfect jacket without destroying anything. It is such a clever solution. So now that we have all the pieces, the conductor, the chemistry, the manufacturing process, let's put it all together. Let's take a quick journey through the high-speed, high-precision manufacturing line that turns a thick metal rod into a finished reel of cable. It all starts as an 8mm thick copper rod. This thing gets violently pulled through a series of diamond dies, stretching it until it becomes as fine as a human hair. Now this process makes it brittle, so it's instantly annealed or heat-treated to make it soft again. Then dozens of these strands are bunched together, twisting at an incredible 6,000 times per minute. The individual cores get their PVC insulation, then they're all twisted together into a single assembly, and finally that rugged outer sheath is applied, and the cable is complete. So, what's the big takeaway here? It's this: that simple, inert object in your wall is anything but. It is a sophisticated product born from decades of debate over global standards, complex polymer chemistry, and manufacturing processes that operate at unbelievable speeds and with microscopic precision. And this quote on screen just captures it perfectly. Far from being a solved problem, this field is a highly mature yet relentlessly evolving industrial discipline. That means engineers are always pushing, always innovating for better safety, more efficiency, and smarter ways to make them. Which leaves us with a final thought. If this much science and this much debate is packed into one simple wire, what other everyday objects are hiding their own worlds of complex engineering choices? Just look around you. You might be surprised by what you find. Thanks for joining us.
Welcome to Learn Tech with S.R. Barak. Let's explore the world of electrical wires and cables together.